We'll end our review now with end behavior, increasing and decreasing intervals, extrema, critical points, and asymptotes. So end behavior, we start with the left side as x approaches negative infinity. So what is the y value doing as this graph continues to go left forever? In this case, the y value is approaching 2. And on the right side, as x approaches positive infinity, the y value is going down forever, so that is approaching negative infinity. The next graph, as we trace left to right, it is increasing first until it gets right there, so the first interval is an increasing interval for x's that are less than -3. Then, for x's that are greater than -3, but less than 1, the graph is decreasing. Then it begins to increase again for x's that are greater than 1. Graph in number 14 has 4 extrema. There's one here, 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 and here. We can't count this because it's open. It never stops getting closer to that point, so there's no discernible point where it actually stops. So right here on the far left, that's not the highest point in the entire graph, but it's a high point for its section of the domain, so that is a relative maximum. And its coordinates are -6, 4. Continuing from left to right, here's the lowest point that you'll see on the graph, except those arrows tell me it continues to go lower on both sides. So that's not the absolute minimum because those arrows say it goes down farther. So that's a relative minimum. And its coordinates are -3, -7. And right here, that's the highest the graph will ever get. There's no arrows that say it's going to get higher. So that is the absolute maximum. And its coordinates are -1, 6. And then right here, that's the highest portion, or the highest point in that portion of the domain. So that would be a relative maximum, and its coordinates are 5, 2. Next, we want to determine what kind of critical point we're looking at. So we need to graph this equation. So we'll graph y equals x cubed minus x squared plus 3. And we don't even really have to look at the graph. What we want to do is look at the table. So first we'll go to table set, so that's second in window. And we'll start at 2/3, our critical point. And we want to keep our change in table at 0.1, so I won't change that. And then second graph shows me the table. I'm going to go up 1. And now I can see outputs on either side of my input. So this output, 2.8519, appears to be lower than the outputs on both sides of it. So that is going to be a minimum. And then we'll graph number 16. 3x cubed minus 18x squared plus 36x minus 23. Table set, and I'll set my table to start at this critical point, 2. Keep my change in table at point 1, and check the table. Up 1 so I can see something on either side. That does not appear correct, so I'm going to go back to y equals and make sure I put that in correctly. I've got 23 cubed. I've got some things in there that need to be deleted. I didn't clear this out. So now, table set, table, up 1, that looks better. So my output at x equals 2 appears to be between the outputs on either side of it, which makes it a point of inflection. And then state the equation of all asymptotes. So for a vertical asymptote, the denominator 5x minus 12 cannot equal 0. So move that 12 over. 5x cannot equal 12. So x cannot equal 12 fifths. So there is a vertical asymptote at x equals 12 fifths. The degrees match. So for my horizontal asymptote, I can divide 17 by 5. So the horizontal asymptote is at y equals 17 fifths. And for 18, set the denominator equal to 0. 4x squared minus 8 cannot equal 0. So move that 8 over. 4x squared cannot equal 8. Divide. X squared cannot equal 2. So x cannot equal plus or minus the square root of 2. So I've got 2 vertical asymptotes. One at x equals the square root of 2. One at x equals the opposite of the square root of 2. The degrees do not match, so I need to make them match. So I'm going to add 0x squared to the numerator. 0 divided by 4 is 0. So there's a horizontal asymptote at y equals 0.